Welcome to solverfy.
Part A of the problem. The first excited state is characterized by n is equal to 2 and the third by n dash is equal to 4. Thus we can write change in energy will be equal to hc square divided by 8 times mc square times L square n dash square minus n square. Then we substitute the value for n dash and n, which is 4 and 2. And we substitute the value for h and c, which is 1240 electron volt nanometer square divided by 5 times the rest mass energy of electron, which is 4511 times 10 to the power 3 electron volt times 0.250 nanometer square is the L value. So this is a 4 square minus 2 square. This will give us 72.2 electron volt. Now that the electron is in n dash is equal to 4 level, it can drop to the lower level, which we call n double dash, in a varieties of ways. Each of these drops is presumed to cause a photon to be emitted of a wavelength lambda, which is equal to hc divided by En dash from energy En dash to energy En double dash, which is equal to 8 times mc square L square divided by hc times N dash square minus N double dash square. Then, for example, for transition from n dash to 4, from 4 to n double dash 3, the photon emitted would be of a wavelength, substituting value for n dash to be 4 and n double dash to be 3. The photon emitted will be, this is 3. Photon emitted will be of a wavelength 29.4 nanometer. And once it is then in n double dash is equal to 3, it might fall to n triple dash 2, emitting another photon. Calculating in this way all the possible photons emitted during the de-excitation of this system, we obtain the following results for part B. The shortest wavelength that can be emitted is 4 to 1, that is 13.7 nanometer. For part C, the second shortest wavelength that can be emitted is I4 to 2, that is 17.2 nanometer. For D, the longest wavelength that can be emitted is I2 to 1, that is 68.7 nanometer. Part E, the longest wavelength that can be emitted is I is equal to 3 to 2, is 41.2 nanometer. For a part F, the possible transition are shown. So there will be for a part F, the possible transition. So let's say this is 1, 2, 3, 4 states. So this is 1, 2, 3, 4. So transition from here to here, transition from here to here, transition from here to here, and we have a transition from, so let me use another color here, from here, and transition from here to here, and transition from here to here, from here to here, and then transition from here to here. Part G, a wavelength of 29.4 nanometer corresponds to a transition from 4 to 3. Thus, it could make either a transition 3 to 1 or the pair of transition 3 to 2 and 2 to 1. The longest wavelength that can be emitted is I2 to 1, which is 68.7 nanometer. Part H, the shortest wavelength that can be next be emitted is I321, that is 25.8 nanometer.